All right, in this podcast, we're going to talk about galvanic cells that are under non-standard conditions. All right, so first off, we need to talk about what does standard actually mean. So standard is defined as the concentrations of the reactants and products, both being 1 molar. Pressure of reactants and products is 1 atmosphere, and temperature is at 25 degrees Celsius. And the standard reduction potential values that we are given in the standard reduction potential table, those are for standard conditions. You always know when something is for standard conditions by looking for this little zero, okay? This little zero indicates this is the value for standard conditions. So all of these things. All right, non-standard conditions. So we take off the little O off Ecell first off. And when we change the conditions from standard, obviously the value of our Ecell or our potential difference is going to change. All right, so I want you to think about this cell. We know that our copper 2 pluses over here are being reduced, okay? So they are gaining electrons, and this electrode is getting bigger. And we also know that over time, the zinc is going into solution as it gives up 2 electrons, okay? So we're getting copper 2 pluses removed, and we're getting zincs added. Okay, so understand that copper 2 plus is definitely a reactant, so losing reactants, and then we're making more of the Zn2 pluses, so that's a product. All right, so here we're given a table, same equation, just gives us some values. So time 1, 2, 3, 4, 5, and what is happening to the concentrations of copper 2 plus and zinc over time. Okay, so hopefully you notice that the reactant concentration decreases as the product concentration increases over time as the reaction proceeds. And if you notice, as the reaction proceeds, your voltage also decreases. All right, so continuing to look at how the Ecell changes throughout the course of a reaction. We already covered that the concentrations of our reactants are decreasing and our products are increasing. That means that our voltage is also decreasing, assuming that we started at standard conditions, obviously. And our voltage is going to continue to decrease until our cell equals 0 volts. When it's at 0 volts, the system is at equilibrium. So Q is equal to K. And the concentrations or the partial pressures remain constant between the reactants and products. So basically, your cell is dead. Your battery is dead. It's no longer got any juice in it. All right, so cells under non-standard conditions are ones that have concentrations of reactants and products that are not 1 molar, that have partial pressures of reactants and products that are not 1 atmosphere, and whose temperature is not at 25 Celsius. The Nernst equation is often used to help us mathematically understand the changes that Ecell undergoes when it's under non-standard conditions. You're not required to calculate Nernst on the AP exam, but you can still, you can be asked general questions about the Nernst equation. All right, understand that this E naught, that's the standard cell potential. RT, so R is the 8.314, and T is obviously going to be whatever your temperature is. Make sure it's in Kelvin. N is the number of moles of electrons from your balanced redox equation. And then F is Faraday's constant, and that is all multiplied times the natural log of the concentration of your oxidized species over your reduced species. Okay, so what does all that mean? All right, so if you look at this chart, we're still looking at that same reaction that we've been looking at. So first thing, it wants to know what is the standard cell potential. Well, obviously, you see it right there. It's 1.1 volts. And then you can also find it right here on the chart. If you'll look, the reactant and product concentrations are 1 and 1 molar for that Ecell standard, or E naught. So if we assign this standard potential as when our Q, so our system when it's not at equilibrium, saying that the Q is equal to 1 when it's corresponding to the standard cell, let's look at what the relationship is between the Q and the cell potential in other cases. So what do we know about when the cell potential is less than what it was at standard conditions? So that's basically in this region, okay? So if you think about Q in this case is just the concentration of your products over reactants. So it's very simple in this one. Okay, so essentially, anytime your products are more concentrated than your reactants, your voltage is going to decrease. So if your Q is greater than 1, then your Ecell value is less than it was at standard. Okay, now conversely, if we looked at question 4 is kind of asking the opposite. So we see that in this region, we have voltages for our cell that are above what we would typically expect at standard. So if you look here, we have reactant concentrations that are higher than the products. Okay, so when your Q is greater than 1, what that means is, not greater than 1, less than 1. So when your Q is less than 1, what that's telling you is that you need to go towards equilibrium, and to do that, you're going to drive that forward reaction really fast, go with it, and so you are going to end up with a slightly higher cell voltage than at standard conditions. All right, so this is basically the word version of the previous slide. So understand that all galvanic cells are spontaneous when our K is greater than 1, okay? And we know that at standard conditions, our E naught cell corresponds to when Q is equal to 1. So as our system is approaching equilibrium, the magnitude of our cell potential is decreasing until our cell is dead. That's when our Q is equal to a K and our cell is dead because our Ecell is now 0. Now, if you look for Q and Q is less than 1, means you need a lot more reactants, so it's going to shift it towards the products, which is going to increase your Ecell output as compared to standard. If your Q is greater than 1, that means that you've got too many products, not enough reactants, so you've gotten too big. So this kind of, I have my wordings backwards here, but you need to decrease the amount of products you've got, okay? Make more reactants. So it's going to shift towards the reactants to make more reactants, but that's a non-spontaneous reaction going in the reverse. So that's going to take away from our Ecell value as compared to standard. So here's a little summary chart. So when Q is equal to 1, we are at E0 cell. Our standard cell potential is given in our reduction potential equation or tables. If your Q is less than 1, then that means that the value of your cell is greater than what it is at standard. And if your Q is greater than 1, it means that your E cell is going to be less than what it is at standard. All right, we can also look at this from a Le Chatelier standpoint. Okay, so if I had this reaction with copper and silver at standard conditions, and then all of a sudden I start throwing in extra silver, okay? So obviously what's going to happen is my silver concentration is going to be above the 1 molar, okay? So it's going to be above my concentration of my copper, which is going to mean that my forward reaction rate is going to increase. And because it's spontaneous reaction, therefore my voltage is going to increase, my electron flow increases, okay? So my E cell is going to be a little bit bigger than it is at standard conditions. Okay, now if I remove the Ag, okay, now I'm shifting my equilibrium back the other way. Now I have less Ag than I do Cu, so my forward reaction rate is going to decrease. And because of that, my voltage is going to decrease and my electron flow current is going to decrease. So I'm going to have an E cell that is smaller than this standard. All right, same thing can be looked at in terms of copper. If you took the same system, added copper, you're adding it to this side. So you're going to need to shift away from it. So you're going to decrease the forward reaction rate, decrease the voltage, decrease your electron flow, so your E cell is going to be less than what it is at standard. Okay, and conversely, if we removed copper 2+, so for removing, it's going to shift this way, which is going to increase your forward reaction, your voltage, and your electron flow, and so your E cell is going to be greater than it is at standard conditions. Okay, a little bit of some short answer questions. All right, so looking at this particular reaction, wants to know what conditions would provide a voltage of the 1.51 volts. Okay, so in order for it to be 1.51 volts, we know that our Q needs to be equal to 1. So what that basically means is that the concentration of our products needs to be equivalent to the concentration of our reactants. Okay, we also need to be at 1 atm because we do have gaseous species here in our reaction, and we also need to be at 25 degrees Celsius. All right, so what could I do to the cell that would increase the potential of the cell? So if I wanted to make the voltage higher than what it actually is, what I could do is I could, number one, I could remove products, okay, or I could add reactants. But essentially, what I want to do is I want to make sure that my products are less than my reactants, okay, in this case. So make sure my Q is less than 1, and it will increase my potential for my cell. All right, now to do the opposite, I would want to add products or remove reactants to shift it back the other way. So I definitely need to have more products than reactants to decrease my cell potential to get my Q to be greater than 1. Okay, so here's another interesting little situation. So we're given a zinc chromium cell and ask if under standard conditions the reaction is spontaneous. So here looks to be my standard conditions. And you do see that we have a positive E cell, which means that it is, in fact, a spontaneous reaction. It does occur. All right, so the estimated conditions that would allow the reaction to be at equilibrium. So remember that equilibrium is when Q is equal to K and your Ecell becomes 0. Okay, so it looks like we are definitely really, really close to equilibrium right in here. So I said that probably the best thing is we need to make sure, so if you look at the concentrations of your chromium and your zinc, okay, it looks like I basically have this one is basically 0.1, right, and then 1. So I need to have 10 times more of the product, so of the zinc 2+, I don't know why I put a 3 there, 2+, than I do of my chromium 3+. Okay, so I need to have 10 times more. My concentration needs to be a factor of 10 greater. All right, is it possible to make the reaction non-spontaneous? So at any point on here, do we get a Ecell value that is negative? And if you look, you sure do. Okay, so in order to make this happen, we basically have a reactant concentration of 0.01 and then a product concentration of 1. So we want our products to be not 20 times, but 100 times. Okay, so I want it to be 100 times more of my zinc than of my chromium. Okay, and that should get me to a non-spontaneous reaction. All right, and then are the data consistent with Le Chatelier's principle? Hopefully you said yes. So you see where it's standard here. And then if I decrease my chromium, okay, so I remove chromium, it's going to shift this way to make more chromium, which in turn lowers the voltage. And that's exactly what happened.